Welcome, Ishika Boys High School students, and a very special shout out to Mr. Jigger's class. You are listening to For the Love of Physics. Okay, so today we're doing a deep dive into something really fundamental. I mean, it's one of those concepts in physics that kind of explains so much.
Yeah, absolutely. It's everywhere once you start looking.
We're talking about the conservation of energy. Our mission, basically, is to figure out what conservation actually means when physicists say it. We'll focus on something called mechanical energy, and we'll see how it, magically stays the same sometimes.
But not always.
Exactly,
Yeah.
and why that happens. So yeah, get ready to see things a bit differently. All right, first things first. This word, conserved. When we talk about something being conserved in physics, it doesn't mean, saving it up.
Right, not like conserving water during a drought.
No, it means the total amount of that thing stays constant. It stays the same within, a specific system you're looking at. Doesn't matter how it changes form or gets rearranged. The total number, the total quantity is fixed.
It's like perfect accounting, basically.
Yeah, exactly. Perfect accounting. Think about mass. You probably learned mass is conserved. Imagine a glass light bulb, nice and whole.
Okay.
Then, oops, you drop it, shatters everywhere, tiny pieces,
A real mess.
a total mess. But here's the cool physics part. If you could very carefully sweep up every single little sliver,
Every bit of dust.
every single bit, and weigh it all together, the total mass would be exactly the same as the original light bulb before it broke. The form changed completely, right? But the total amount of stuff, the mass, was conserved.
And what's really fascinating there is how it points to this underlying order. Things look chaotic, they break, they transform,
Yeah.
but some fundamental things like mass just hold steady, the universe keeps track.
A cosmic ledger. I like that. Okay, let's test this idea. Money. Is money conserved in your pocket?
Definitely not in mine.
Right. You spend some, maybe you find some. The total amount goes up and down all the time. But imagine a magic wallet.
Yeah.
You start the day with $1.
Okay, magic wallet.
Mm.
I'm listening.
And no matter what, you always have $1 in there. Maybe it turns into 4 quarters.
Mm-hmm.
Or 10 dimes.
Hmm.
Or 100 pennies. Or some weird mix. But if you count it all up, it's always exactly $1.
Ah, I see. The total value is fixed, even if the coins change.
That's conservation. The total quantity stays the same even if the form is totally different.
It's a really key difference. Money flows in and out of your personal system. But these physical quantities, like mass and like energy, which we're getting to,
Right.
they don't just vanish or pop into existence from nothing. They just change costumes.
Change costumes, yeah. Okay, so we got conserved down. It means the total stays the same. How does this apply to energy? Now, you already know about different energy types, right? You've got kinetic energy, that's the energy of motion.
Like a baseball flying through the air.
Exactly.
Yeah.
And you've got potential energy. That's stored energy.
Stored how?
Well, maybe because of its position, like a book held high up.
Gravitational potential energy.
Right, or stored in its state, like a stretched rubber band or a compressed spring.
Elastic potential energy.
Perfect. So lots of physics situations, and real life too, involve these energies swapping back and forth. Think about an old grandfather clock with a pendulum.
Okay, the swinging weight.
Yeah. As it swings, it's doing this constant energy dance. At the very top of its swing, it stops for just a split second.
No motion.
No motion, so
Good.
zero kinetic energy right then. But it's high up, so it has maximum gravitational potential energy.
Got it.
Then, as it swings down, it speeds up.
Right. Losing height but gaining speed.
So its potential energy goes down, but its kinetic energy goes up. It's transforming.
And in a clock, you might also have springs involved, storing elastic potential energy too.
True. So you've got all these different energies interacting, which brings up the question.
Yeah, how do we talk about all of them together when we're analyzing movement?
Exactly. And physicists have a way. We define something called mechanical energy. Now, super important. It's not some brand new type of energy. It's more like a category, a useful label.
Okay.
Mechanical energy is simply the sum of an object's kinetic energy, plus all the relevant potential energies acting on it.
So Ke plus Pe.
Right.
Or Pes, plural.
Right. For the pendulum, it's kinetic plus gravitational potential. If a spring was involved, you'd add the elastic potential too. You often see it written like ME, KE plus CPE.
Ah, the sigma.
Yeah, that Greek letter energy just means sum of. It's a reminder. Add up all the potential energies that matter for the situation.
That makes sense. It groups the energies related directly to motion and position. And it's useful to remember, like you said, it's a category. There are other energy types out there.
Oh, yeah.
Things like nuclear energy, chemical energy stored in bonds, the internal energy of atoms jiggling around which we feel is heat, electrical energy. We often group these under the banner of non-mechanical energy.
Right. Stuff not directly tied to the big picture movement or position.
And while those are super important in the universe, for a lot of the motion problems you start with in physics, you can often focus just on the mechanical energy changes, assuming these other forms aren't really part of the exchange yet.
That's a really good point.
Yeah.
It lets us simplify things to understand the basics of motion, which brings us neatly to the main event, the big rule. The conservation of mechanical energy.
Okay, the core idea.
This is super powerful. It says that in many situations, the total mechanical energy is conserved, meaning the mechanical energy you start with, ME initial, is exactly equal to the mechanical energy you end up with, ME final. So ME initial, ME final. It's elegant.
So there's a catch, right? You mentioned something.
There is a very important condition. This beautiful conservation rule works mainly when we can ignore non-conservative forces.
Sure.
And the big one, the most common one you'll deal with, is friction.
Friction, the spoiler.
The spoiler, exactly. We'll talk about friction's role in a minute because it's crucial for the real world. But first, let's stay in this ideal frictionless world for a bit. Let's picture it. An egg, sitting on your kitchen counter, maybe about 1 meter high.
Okay, breakfast is on the line.
Totally. And it rolls off the edge, just falls. Ignore air resistance for a sec.
Ideal egg falling.
Ideal egg. As it falls down, its height gets lower.
So its gravitational potential energy decreases.
Yep. But what happens to its speed?
It speeds up.
Yeah.
Increases. So
Yeah.
kinetic energy increases.
Right. One goes down, the other goes up. But here's the conservation part.
What's really cool about this, connecting back to the total, is that if you could measure both PE and KE at any point during the fall.
Yeah, like halfway down, or just before it hits.
Exactly, any point.
Yeah.
And you add them together. That sum, the total mechanical energy, stays constant. For a typical egg falling from 1 meter, maybe it's around, say, 0.74 joules.
Wow.
And it stays 0.74 joules all the way down. The energy just shifts its form from potential to kinetic.
It's just converting.
Precisely. Total amount is conserved. Same thing if you threw it upwards. KE would convert back to PE, but the total ME stays the same. Until splat.
Okay, yeah, let's not think about the splat. But that constant total is amazing. Now, here's where it gets, like, really useful and kind of mind-bending. Imagine a kid on a slide at the park, but it's a magical frictionless slide.
Okay, very slippery slide.
Super slippery. The kid starts from rest at the top, maybe 3 meters high. Now, because there's no friction, we know mechanical energy is conserved.
ME initial, ME final.
Exactly.
Yeah.
So all that potential energy the kid has at the top.
Because they're high up, but not moving yet.
Right. It all gets converted purely into kinetic energy by the time they reach the bottom.
Okay.
And here's the amazing shortcut. You don't need to know how twisty the slide is. You don't need to calculate forces and acceleration at every point.
You just compare the start and the end points.
Yes. Just compare the energy at the top, all potential, to the energy at the bottom, all kinetic. It makes solving the problem so much simpler.
It's incredibly powerful. And it leads to a question, something that often surprises people.
What's that?
Did you know, when you actually write out the math for this, setting the initial potential energy equal to the final kinetic energy,
Yeah.
the mass of the child, it cancels out. It disappears from the equation.
Wait, really?
Really. It means the final speed of the child at the bottom of that frictionless slide. It doesn't depend on how heavy the child is.
No way. So a little kid and a bigger kid.
Sliding down the same frictionless slide from the same height,
Uh-huh.
they reach the bottom with the exact same speed.
That's wild.
It is. It connects right back to Galileo and objects falling at the same rate, regardless of mass. When you ignore air resistance, same
Yeah.
principle at play, just with energy.
Mind blown.
You
Okay,
have-
that's profound. So frictionless world, mechanical energy is conserved, mass cancels out on slides. Pretty neat.
Yeah,
But we live in the real world,
we do. And the real world has friction.
everywhere. So what happens to our lovely conservation of mechanical energy rule then? That condition in the absence of friction is kind of a big deal.
It is, because in most real situations, mechanical energy is not conserved.
Okay, so the rule breaks down.
Well, the mechanical energy conservation rule does. Friction messes it up.
How? Let's take an example. Sanding wood.
Okay, yeah. getting splinters smooth?
You take a block, maybe with sandpaper, and you rub it back and forth on a rough piece of wood. You have to keep pushing it, right? To keep it moving, even if it's moving at a steady speed. Why?
Good question. Its kinetic energy isn't really changing much if the speed is constant. And its height isn't changing, so potential energy isn't changing.
You're right. So where's the energy you're putting in going?
What's happening there is friction is doing work. It's acting against the motion. And that work done by friction is basically converting the kinetic energy you're trying to give the block into other forms, non-mechanical forms,
Like what?
mostly heat. That's why when you sand something, both the block and the wood get noticeably warmer.
Ah, okay. So the energy isn't vanishing.
Not at all. It's just changing costume again, remember.
Right.
It's transforming from kinetic energy, which is part of the mechanical total, into thermal energy, the jiggling of atoms, which is non-mechanical.
So from the viewpoint of just ME equals KE plus PE, the mechanical energy seems to decrease. It looks like it's being lost or dissipated.
Exactly. Dissipated is a good word. It's spread out as heat, maybe a little bit of sound too.
And this is the really, really crucial bit,
Right?
right?
It's totally fundamental.
Even though mechanical energy isn't conserved when friction is around, the total energy of the universe is always conserved. Always. No exceptions found.
That's the first law of thermodynamics in action. Energy cannot be created or destroyed, only transformed from one form to another.
So the energy from the sanding block didn't disappear, it just turned into heat, warming up the block, the wood, and maybe the air around it slightly.
Precisely. The total amount of energy in the universe stayed exactly the same. It just got rearranged.
Okay. That's a huge concept. Mechanical energy is useful, often conserved without friction, but total energy is always conserved.
You got it.
Phew. Okay, let's try and wrap this up. What did we cover in this deep dive? We dug into the conservation of energy with a special focus on mechanical energy.
Yep.
We learned conserved means the total amount stays constant, even if the form changes, like the mass of that poor shattered light bulb.
Right.
We define mechanical energy, remember, it's just a category as the sum of kinetic energy and all the relevant potential energies. KE plus Phi.
The motion and position energy.
And the big rule, mechanical energy is conserved. ME initial, ME final, but only if.
Only if there's no friction or other non-conservative forces doing work.
Exactly, that's the ideal case, like the frictionless slide. But even when friction is present and mechanical energy gets converted into things like heat,
Like with the sanding block.
the total energy, all forms combined, is always, always conserved. It just changes its disguise.
Perfect summary.
Okay.
Which leads to maybe a question for you listeners to think about.
Okay, hit us with it.
All right. Think about a basketball. You drop it, it bounces on the court a few times. Is the mechanical energy of that basketball conserved during the entire process of bouncing? Why or why not? And if it's not conserved, where do you think that mechanical energy goes? What other energy forms get involved in a bounce?
Ooh, that's a good one. A bouncing ball. Lots to think about there. Okay, we really hope this deep dive into energy conservation helps things click for you in physics class. Hope it helps you see energy transformations happening all around you. Stay in contact with your physics teacher. Stay creative.